Hi, and welcome to a lecture on directivity of arrays of current moments. So first, let me remind you about the electric field intensity, which is radiated by a single isolated current moment. The idea here is that the current moment is both displaced from the origin and oriented in an arbitrary direction, and the mathematical description of such a current moment then is given by this expression, in notation that we've discussed in another lecture. And the associated radiated electric field is given by this expression under the assumptions that the field point is far from the source point in terms of wavelengths, and also that the distance to the field point is much greater than the distance to the source point. So under those assumptions, we get this expression for the radiated electric field of an arbitrarily oriented and displaced current moment. Now, we want to use this as the building block for an array, and in fact this serves as an appropriate building block for virtually any transmitting array, because we can model the radiating currents from just about any array as a superposition of these current moments. So let's begin with some simplifying notation. The electric field intensity from the nth current moment, because we will have many of them, is given by E sub n. The subscript n indicates or enumerates the current moments. Theta hat prime sub n, because each one of these current moments can be oriented in an arbitrary direction, and it might be a different direction. A factor k, which absorbs a whole bunch of constants that, while important, we don't necessarily want to bring along or have to keep writing over and over again. So the factor k is defined as j times eta, the free space impedance, times beta, which is the phase propagation constant, times delta L divided by 4 pi. Just consolidating constants. What's left over is I sub n, which is quite important because that describes the excitation. Sine theta prime n. And once again, the subscript is n because each one of these current moments could be in a different direction. This phase pattern description, e to the plus j beta p sub n dot r hat. And once again, each one of these current moments is a different location, so it's p sub n. N is enumerating those current moments. And then finally, e to the minus j beta r over r, the spherical wave dependence, reference to the origin. And note here that I'm using the equal sign here, but it's really still an approximate expression. I'm simply trying to avoid being tedious. The approximations still apply. So the field radiated by capital N such current moments, enumerated 0, 1, up to n minus 1, again counting like C programmers, is given by this quantity, E, argument R, which is the field point, which is simply the sum from n equals 0 to n minus 1 of these contributions from each one of the current moments. We'll pull out the factor k, which is in common to all of the current moments, and we'll also pull out the factor e to the minus j beta r over r, because that's common to all the elements. And what's left is a sum from 0 to n minus 1 of this much. We can interpret that as the pattern, that is the magnitude phase, right? Because that's all the information contained there. It doesn't say anything about the distance to the source. It doesn't say anything about the distance to the field point. It doesn't talk about the spherical phase front. It is simply describing an evolution of magnitude and phase with theta and phi. So at this point you might ask, what about mutual coupling? Don't the elements of an array interact? Shouldn't these currents interact? And the short answer for the purpose of this analysis is no. And the reason is because in an implemented transmit array, the radiation is due to response currents, which are different from the currents that you would apply, and the difference is due to the mutual coupling. In other words, you apply currents, but the currents which radiate are the sum of the currents that you applied and the currents which are induced due to interactions among the elements. Here we're simply talking about the currents that result in that whole process and which radiate. Another way of saying this is that mutual coupling, if it's significant here, has already happened. So we're not neglecting mutual coupling, we're just considering what's happened after mutual coupling. The question of how to get the response currents from the applied currents, or from applied voltages, or however you are driving this array, when mutual coupling is significant, is a topic for another lecture. So no need to worry about it here, and we're not overly simplifying anything. To continue, recall that theta prime sub n is given by an expression we've previously worked out, arc cosine z prime hat n dot r prime hat n, where in this case r prime hat dot n is the position of the field point minus the position of the current moment, and then dividing by the magnitude to get a unit vector. Now just note that our original expression presumes that the distance to the field point from the origin is much, much greater than any distance within the array. So there's really no additional assumption required to say that p sub n is p sub naught. In other words, it really doesn't matter which element in the array I've got here. They're all approximately equal. For the purpose of computing this unit vector, I might as well just use p sub naught. So I'm going to give that a name. It's r hat prime sub naught. So this is simply recognizing the fact that all these unit vectors, even though in principle they're different for each element in the array, in fact they are so close to being parallel under this assumption that I might as well just use one. And the one I'll use is for the reference element, the one I've identified as n equals 0. Okay, now an important special case. All currents pointing in the same direction. In other words, I'm arbitrarily now requiring all the current moments to point in the same direction. It's not necessary, it's simply that it yields a dramatic simplification and it corresponds to a very broad class of problems. I'm saying that if the 0th current moment looks like this, then all the other current moments are pointing in the same direction. Now they might be in different locations. There's no statement here about what their positions are. We're just saying they're all pointing in the same direction. And in that case, r prime hat sub n is equal to r prime hat sub naught. All of them are equal to that of the reference or the n equals 0 element. And in that case, theta prime sub n is equal to theta prime sub naught, where that's equal to r cosine z prime hat sub naught dot r prime hat sub naught. And similarly, theta prime hat sub naught is given by this expression, which was worked out in a previous lecture. But we might as well just use the reference element because the assumption applies about the pointing all being in the same direction. So all this reduces to just one unit vector describing the position of the field point relative to the orientation of the current moment. And again, the reason we're doing this is not because we have to, but simply because it yields a dramatic simplification and it corresponds to a very broad class of problems. Subsequently, under these conditions that we've applied, the total electric field intensity will be given by K theta prime hat sub naught, the magnitude part of the pattern function, which is sine theta prime sub naught, e to the minus j beta r over r, the spherical wave dependence. All those things are the same for all the elements, so we've separated them out. What varies from element to element, we leave inside the sum. The sum is from n equals 0 to n minus 1, I sub n, and then this phase dependence, which depends on the precise position of the current moment within the array. Now just pause for a second and compare this result to the single current moment result. In other words, if we just take n equals 0, and write the expression for the electric field intensity for that one element in the exact same format, well, we get something which is identical except in one place. What's different is right here. It's simply one term out of that sum, namely the 0th term. This motivates the definition of what we call the array factor. So in this case, the array factor is defined as the sum from n equals 0 to n, I sub n times that pattern phase function. If there's only one element in the array, we just get that one term. Otherwise, we add all those things up. So now we can describe the radiated electric field of the entire array as k times theta prime hat sub naught times the array factor, magnitude, pattern function, spherical wave dependence. Another way of saying all this is the array factor can be viewed as the pattern of an array of isotropic elements located at the element positions. The array factor is the pattern of an array that consists only of isotropic elements. Alternatively, you can think of the array factor as the contribution of the array geometry, that is, the element positions, and the excitations, that is, the currents, to the total field of the array. The array factor is a way to think about the effect of just those two things independently of other considerations, in particular, the patterns of the elements. With that in mind, it is convenient to think of the total radiated electric field intensity as that of a single element, in this case I've chosen the reference element, n equals 0, times the array factor, divided by an array factor for an array consisting only of the reference element. And this is known as the principle of pattern multiplication. We say that under the conditions that we have imposed here, the radiated electric field is equal to the radiated electric field of just one element. Again, all the elements have the same orientation but different positions. And then separately, we can account for the array, the number of elements, where the elements are, and so on. And that's what's going on here. That's pattern multiplication. Okay, now we're ready to calculate the directivity of the array. So as usual, and this is the default strategy, the approach is to first calculate the power density. You get that from the expression for the radiated electric field intensity. You calculate the total radiated power. You get that by integrating over a sphere in the far field of the array. You calculate the power density averaged over all directions, which is usually just a matter of dividing by 4 pi r squared. And then the directivity is a ratio of those two things. Remember, directivity is the power density in a specified direction divided by the power density averaged over all directions. Okay, so let's go ahead and do it. So here's step 1, calculating the power density in the far field, given by the plane wave expression, magnitude of the electric field intensity squared divided by 2 divided by the wave impedance. In this case, we end up with magnitude k squared divided by 2 eta, magnitude of the array factor squared, sine theta prime naught squared, 1 over r squared. Also, I should just remind you here, this factor of 2 here is indicating that we're using peak and not RMS units for the electric field intensity. If you're using RMS units for the electric field intensity, that 2 would disappear. Step 2, the radiated power. For that, we simply integrate the power density over the sphere. That's an integration from 0 to pi and 0 to 2 pi. And I'll note here that this is easiest to do in the rotated coordinate system of the reference element. It really doesn't matter what coordinate system you do it in, but we've already got theta naught and phi naught in the primed coordinate system, so we might as well just integrate over the primed coordinate system. It's only important that that sphere enclose the array, so here it's just easiest to use the primed coordinates. Here's the expression for the power density, and then here is ds. So working that a little bit, we end up with magnitude k squared divided by 2 eta out front as a constant. And then inside the integral, we have magnitude of array factor squared, sine theta prime naught cubed, d theta naught prime, d phi naught prime. Step 3, compute the average power density. That's just the total power divided by 4 pi r squared, the area over the sphere. So that's super easy. We get this expression highlighted here. And then step 4, we divide power density by average power density to get directivity. So this is simple substitution in the numerator and in the denominator, yielding the expression that I have put in the box right here. After eliminating values that appear in the numerator and denominator, and a little bit of cleanup, I get 4 pi times magnitude of array factor squared times sine prime theta squared divided by this integral. Now be careful here. The numerator is a function of theta and phi, and I've expressed it in theta prime and implicitly in phi prime as well. So beware of mixed coordinate system. Usually is not a problem, but it can be a point of confusion if you're not careful. Also note that the denominator reduces to a constant when this integral is evaluated. So the numerator will be a function of theta and phi, or equivalently theta prime and phi prime, whereas the denominator will always reduce to a constant. Now, frequently we are interested in the maximum directivity. In fact, when many people use the term directivity, they mean the maximum directivity. That is, the directivity in whatever direction it's the greatest. So let's see how that works out. Let the direction in which the directivity is greatest be given as theta prime naught max, and similarly phi prime naught max. Then this expression becomes the highlighted expression here. At this point, it becomes convenient to define a thing that we're going to call the normalized pattern function, f theta naught prime phi naught prime. The normalized pattern function we are going to define to be the array factor times sine theta prime naught, divided by the numerator again, but evaluated in whatever direction the directivity is maximum. So this is normalized. We call it normalized pattern function. It's normalized in the sense that the magnitude of this thing has a maximum value of 1. And you'll see why that's convenient by comparing what you have here to what we got in this expression. If we make the substitution and wiggle things around a little bit, we find that the directivity, that is the maximum directivity, can be written as 4 pi in the numerator, divided by integration over the sphere of the magnitude of the normalized pattern function times sine theta prime naught d theta prime naught d phi prime naught. Again, the value in the denominator is a constant, and we refer to this constant by a special name. We refer to this constant as the beam solid angle. You can see from dimensional analysis that the units of this thing in the denominator, the beam solid angle, has units of steradians, that is solid angle, hence the name. So to clean this up a bit, we can say that the maximum directivity is simply 4 pi divided by omega sub a. That's what we're calling the beam solid angle. You can now appreciate why we like to do this, because this gives us a very simple interpretation of directivity. It's simply 4 pi, the number of steradians in a sphere, divided by the beam solid angle, which is another way of talking about the directivity of this thing. To make sure we're thinking straight here, let us now check and demonstrate this result by applying it to a simple known case. And that is simply the good old z-directed current moment. We've already worked out what the directivity of a z-hat directed current moment is, so we should be able to get that same result by using the procedure above. No question, it's a long way to do it, but it will demonstrate the technique and confirm that we get the right result. So, for a single z-directed current moment, the array factor, which in general is this thing, is in this case, where n equals 1, because there's only one element, given by the single term. And we might as well put that element at the origin, that is p naught equals 0, in which case the array factor is simply I naught. And in this case, the normalized pattern function, which in general is defined to be this thing, in this special case, just reduces to I naught times sine theta in the numerator, and I naught times 1 in the denominator, which is simply sine theta, which makes sense. The normalized pattern function is simply sine theta, and we already know that to be true for the z-directed current moment. The beam solid angle, in general, is given by this expression, and making the substitution here, first note that we might as well do this in the unprimed coordinate system. Magnitude of the normalized pattern function, sine theta d phi. We can factor this into two integrals. It's this integral over theta, this integral over phi. The integral over phi is immediately recognized to be 2 pi. The integral over theta is a pretty well-known definite integral. You can work it out for yourself, but I will tell you the answer is 4/3. So we find that the beam solid angle of the z-hat directed current moment is 8/3 pi steradians. And then finally, to get the directivity, that's this 4 pi divided by beam solid angle. That is 4 pi over 8/3 pi, which is 3/2, which is 1.5, which is 1.76 dBi, as expected. So hallelujah, this all checks for the special case of a z-hat directed current moment. Now, of course, the intended use for all this is for arrays of arbitrarily large numbers of current moments. And so that's a topic for a different lecture. But for now, at least we know this theory survives this simple check. That concludes this lecture on the directivity of arrays of current moments.